This is the 1-3 experimental design notes for statistics. This is the third section and the last one for this unit. We're going to cover TEKS 2A, 2B, and 2C. So what you should learn is how to design a statistical study, how to collect data by doing an observational study, performing an experiment, using a simulation, or using a survey, and how to create a sample using random sampling, simple random sampling, stratified sampling, cluster sampling, and systematic sampling, and how to identify a biased sample. Okay, I'm going to turn this off because it always blocks the rest of the slides. So directions in your notes, copy the notes from the starred slides and any examples that you feel will help you. You will answer questions in Edpuzzle as you go through the video, and this counts as your journal grade. So here's the first slide. You'll definitely want to copy. Notice there's a star in the bottom right-hand corner. So guidelines for designing a statistical study. These are the steps you would go through if you were starting a study and going all the way through all of the different steps. First of all, you would identify the variables of interest. What is your focus? And then you would pick and the population of the study. So for instance, if your population was Temple High School and you wanted to, the variables might be junior class, senior class, freshman class, and sophomore class. So those would be the variables, or something else similar to that. And then you would develop a plan for collecting the data. Are you going to do a sample? Are you going to do a survey? Are you going to watch people? Are you going to do an experiment? Or are you going to use a simulation? If you use a sample, make sure the sample is representative of the population. You would not pick 100 people to represent the entire population in the United States. That would be silly. It's too small of a sample. Then you collect the data using the method the plan you decided on. You would describe the data using descriptive statistics techniques, some kind of charts. You would do some kind of statistical analysis using some of our mean, median, mode, that kind of thing. Then you would interpret the data and make decisions about the population using inferential statistics. And then you would identify any possible errors that you might have had. This is where most people make mistakes. They forget this last step. Error, we are all humans, and there are always potential errors that could happen. So you want to always make sure to identify any errors that might pop up. So data collection. There are 4 types. The first one is an observational study. This involves a researcher observing and measuring characteristics of interest, but does not, repeat, does not interact with the subjects when being observed. The environment is not changed. An example of this would be, say you stood at one corner of the cafeteria and observed how many people were drinking their chocolate milk versus white milk. You would not go up and ask people, you would not interfere with them in any way, and you would not influence them on whether or not they should drink chocolate or white milk. It would just be a watching thing. The next one is a simulation. A simulation is the use of a mathematical or physical model to reproduce the conditions of a situation or process, especially when the process is too dangerous or expensive to be done as an experiment. An example of this would be creating a game that would simulate a virus being spread across the world. Obviously, if there wasn't one really actually doing that right now, we would not want to actually release a virus into the environment and then see how it happened. We would use a simulation to kind of give an idea of what kind of things could happen. It is always better to do something safe when it doesn't interfere or hurt other people with using a simulation. The next one is an experiment. This is a treatment is applied to part of a population and responses are observed. Another group, called a control group, is observed without the treatment. Results are compared. Right now, during the virus, vaccines are being developed by various companies all over the country and all over the world, and they are involved in experiments. They are on stage 2 for most of them, where they are giving the vaccine to a to a specific group, a treatment group. In a second group, they're giving basically a fake shot, the control group, and then they're observing the differences between the reaction to of the body or the virus to the vaccines. So that's an experiment. The last is a survey. This is an investigation in one or more characteristics of a population. Some examples are conducting a census or a poll using a sampling of the population. Currently, your parents will have had to have filled out a U.S. Census report. Now, under federal law, everybody in the United States is required to fill this out. However, some people do not. The census is actually meant to give the United States government an idea of the U.S. population, not just a count, but also characteristics such as employment and pay and stuff like that. However, even though it's required by law for everybody to fill it out, there are some people who refuse to fill it out, and doing so means that we are basically pulling a sampling of the population. However, because majority of people actually do fill out the census, the sampling is really good because it's basically like 90% or so of the population actually does what they're supposed to do. Okay, sampling techniques. So a random sample is one in which every member of the population has an equal chance of being selected. For instance, if there is 100 people in the population, they each have a 1 in 100 chance of being picked. There's nobody that gets preferences. A simple random sample is a sample in which every possible sample of the same size has the same chance of being selected. So that 100 people, you can break them up into 10, randomly select them into small groups of 10, and each actually small group would have an equal chance of being picked. To take a simple random sample, there are a couple of different ways you can do it. The first is to assign, and this is for either one, assign each member of the population a number. And then you use either a randomizer or what we call a table D chart to determine which members of the population will be chosen for the sample. And you continue the process until you populate a sample of the size you want for the experiment, the survey, the simulation, or the observational study. Sampling techniques. A type of sample that often leads to biased studies so that it is not recommended is a convenient sample. A convenient sample consists only of available members of a population being sampled. So an example would be you stand outside of Walgreens, ask people if they're going into Walgreens, what kind of medicine are you buying? And then you mark down what their medicine choice is. It's a convenient sampling because you already know a lot of people that go to Walgreens, they're going there really for medicine. It's biased because it is targeting a specific type of thing. If you stood outside of, say, Walmart, you'd have a much better chance of having a little bit more of a unbiased study because Walmart has more than just really medicine as potential things that you would buy there. So that's kind of the idea. But again, even standing outside of Walmart would be a convenient sampling because you're still targeting people that are going into Walmart already purchasing something. If you really wanted to do a survey that would be as unbiased as possible, you would have to do it in a way that randomly selects a small sample of the population, send out the survey, and basically include in that survey where would you shop or where do you shop for medicine, what kind of medicine you would have, and such. So you would have to make it as untargeted as possible. Anything that is targeting a specific thing, a group of people, and just basically standing there asking the question, that's a convenient sample. Okay, stratified samples ensures that the members from different groups are equally chosen. So for instance, you choose 100 random members of each town within a specific county. The population is everyone within the county, but each town is a unique group. By choosing 100 random members from each town, you get a stratified sample of the entire county. Another example with that, at Temple High School, if you were to pick, say, 15 students from each of the grade levels. That would be a stratified sample. As long as everybody in each grade level had an equal amount of chance of being picked, then your stratified sample would be random, but you would be picking from each individual group. So like basically you take all of the freshmen and stick them into the freshman cafeteria, all the sophomores and stick them in the gym, all the juniors and stick them in the auditorium, and all the seniors and stick them in the senior level or the senior cafeteria. And then from those locations, randomly pick the 100 people or the 15 people or something like that. But everybody that's in that room has an equal chance of being picked. The cluster sample allows a selection of a group or zone within a group of members that have similar characteristics. So in this case, they are things like males and females kind of thing. An example would be choosing a specific period of 6 sections of the same course as the sample. So within, you pick 6 different sections of, say, algebra. There's several different teachers on campus that teach algebra, so there's a lot of class periods to choose from. You would randomly pick 6 of those class periods. And then systematic sampling, members of a sample are selected at a specific interval, such as every 5th person or every 10th person. So this one is not as random as the clustered or the stratified. It is actually more of kind of a convenient sampling because it is it's not as random. It's more of a you're randomly picking the number that you're choosing, but after that, it's basically you just keep on picking every 10th. So if you happen to have a production line where the computer or something glitches every 5th person, and you happen to pick the fifth item every time, you're going to see a higher amount of problems with that product than say if you randomly have picked 5th, 7th, 10th, 12th, and all that kind of thing. Okay. Techniques used in unbiased results to get unbiased results in experiments. We use something called blinding. It's a technique where subjects do not know whether they are receiving a treatment or a placebo. In that case, the doctor or the person doing the experiment knows which subjects are receiving it, but the person receiving it does not know. A double-blind experiment involves where both the experimenter and the subjects don't know. So a great example is there's a TV show called House where they did an episode where one of the doctors was was in a study, and the nurse actually was commented to the experimenter, "Doesn't it stink?" Because the actual medicine stunk, where the placebo did not. And by accident, the experimenter found out that the subject actually was not receiving the treatment. She was receiving the placebo. Ultimately, that can happen. It does happen once in a while where the experimenter accidentally finds out the situation. But as long as the experimenter does not reveal that they already knew, then the results are valid. Ultimately, after the experiment is over, the experimenter is informed once all of the data has been collected. So eventually that person that's doing the experiment figures out who's who. But during the experiment, in a perfect world, they wouldn't know at all. Okay, so matched pairs design, subjects are paired up according to similarity. One subject in the pair is randomly selected to receive the treatment while the other receives a different treatment. So example is you'd pair up people, a male and a female, that are basically the same age or something like that. And then one of them would receive treatment when the other would not. Generally, they don't mix the sexes though, simply because males and females have a tendency of reacting differently to medicines in a lot of ways. So it would maybe be two females of the same age or 2 males of the same age. Okay, randomization is a process of randomly assigning subjects to different treatment groups. You would want to make sure that as much as possible, it's a random blend. Randomized block design, it divides the subjects with similar characteristics into blocks, and then within each block, you randomly assign the treatments. So again, you block them off by, say, age, and then within that age group, you would randomly assign treatment, placebo kind of thing. And it's not this person and then the next person's that it is done, but with, like I said, a randomizer or computer technology or something like that, that randomly picks the people 1 through 30, and it could be 1, 10, 17, 20, 30 that actually gets the treatment, and the others get the placebo. Okay, so sample size and replication. Sample size is very, very important. Sample size, lowercase n, is the number of subjects in that sample. Okay, if there are too few samples in a sample, too few subjects in a sample, then there is not enough information to make a general statement about the population. Sample size, usually you try to stick with at least 10% of the population. So if your population is 1,000, then you try to get 100. The smaller the sample, the less the study is going to talk about the full population. So you would not take 10,000 people and do a study on 10,000 people and then make an assumption about the entire United States. It's one of the reasons why polls, presidential polls, are actually not very accurate, especially if they're national polls, because they don't interview that many people. There's like maybe sometimes as much as 10,000 people, but they're trying to make an assumption about the entire population of the United States. Not really good statistics. Okay, what is replication? Replication is the repetition of an experiment under the same or similar conditions. Once a researcher does an experiment, they will publish their findings. They expect that other people can go back and repeat the experiment and get the same or similar results. If that happens, then it validates the original experiment. If it doesn't happen, then they need to go back and see what was the change, what made something different, where was the issue. And if it never gets replicated, then the scientific world doesn't see it as being valid at all. If a study cannot be repeated, then the results are less likely to be accepted by the scientific community. Okay, so we're going to do some example problems of trying to decide which type of data collection method you would use. So first one is a study of the health of 213 seasonal flu patients at a hospital. So is this an observational study, an experiment, simulation, or survey? If you chose survey, you'd be right. The reason for that is all of the patients are accessible and the number of patients is small enough. So 213 patients is not too many people to do a survey and get the information. And they're all at the hospital, so it would be easy to collect the information. Next one is a study of the effect on the human respiration system of a new oxygen delivery system for deep sea divers. Which one would this be? If you chose experiment, you'd be right. You want to measure the effect of the respiration system based on the new product. So basically, they would take the respiration rate prior to using the new system, then they'd have them use the new system, and then they take the respiration rate afterward and compare them. So they would do an experiment. They would probably have maybe 15 people actually doing the experiment, and maybe another group of people using the old system and then compare the results. So that would be an experiment. It would still use a small number of people for the sample, but you would be able to use a comparison process. So next is a study of the effect of expanding the freeway system on traffic congestion in a major metropolitan city. So which of these would it be? If you chose simulation, you'd be right. It is impractical, costly, and time-consuming to complete this in real life. In fact, it would be very dangerous to try to make the change, do a trial and error, hoping that nobody gets hurt. So it's very, very costly to do that kind of thing. So instead, they use a simulation system, something like SimCity or something like that, that they could kind of see, okay, if we build it this way, this is what we expect the flow of traffic would look like based on what we know it does now, and it has done in the similar type systems in other cities. And then they would decide, okay, well, this is the best option with the least cost. Okay, the last one is a study of how the eating habits of toddlers change when they are getting new teeth. So again, is this an observational study, an experimental, simulation, or survey? So here would be an observational study. You would want to observe and measure certain characteristics of part of the population. So basically, you're going to watch the toddlers have eating as they're eating right about the time when they're starting to get their new teeth and observe facial expressions. Um, do they shy away from certain types of foods, like certain hot foods or cold foods? Those are the kind of things that you would do, but you would not be interacting with those toddlers. You would just be watching them. And that is okay. So there's one more thing about notes we need to look at. That's factors that can ruin experimental results. So when you're doing an experiment, there are two things that can ruin results. One is called confounding variables. This occurs when the experimenter cannot tell the difference between the effects of different factors on a variable. So, for instance, you do an experiment for a new headache medicine, and the results that come in, the responses to the questions that might, after questions might be ambiguous because the person might have turned out the lights. Well, that could have affected whether or not their headaches went away, or it could have been that maybe they were taking multiple types of medication and they're interacting differently than was expected. Those kind of things are confounding variables, and they make the results very difficult to interpret. A placebo effect occurs when the subject reacts favorably to the placebo when in fact they're not getting the medication at all. This happens quite often in medical experiments, and what it basically boils down to is your mind is a lot stronger than you think it is, and it sometimes gives you that reaction that you think you're getting better when in fact you're not. Back to my example from House, that same situation, the doctor who was involved in the actual study and was receiving what she thought was a medication was actually receiving the placebo, but she was reporting improved motor skills and other types of memory type things that you would expect to be happening if you were getting better. But in fact, it was all about positive thinking. She thought she was getting better, so she felt like she was. It wasn't necessarily a she was getting better thing. The medicine, her disease wasn't actually going away or wasn't actually being affected. It's just her positive thinking was making the difference. So the placebo effect sometimes gets reactions from the non-treatment patients, the subjects that emulate what the medicated people are doing, but are not necessarily actually making any changes. So that's what the placebo effect is, and that sometimes can skew the results because then begs the question: did the medication actually make any difference, or was it some other factor, a compounding variable possibly, that was affecting both the treatment group and the placebo group that could be explained why they both were getting better at the same time?